For applied optimization problems in calculus, the initial setup is a primarily algebraic manipulation just to get an objective function, a function that we want to maximize or minimize, into a function that just has one variable, and also to be able to assess what the reasonable domain is for that variable that the function has. And so for this example, it's actually going to be a two-part example. The object is going to be the same for both of the parts, but we're going to show how the different setup is based on what it is we're given and what we want to find. And so what we need to do here for these problems, we don't need to go completely through the calculus to get final answers, but they're stated still as calculus problems. And the goal here for these particular problems on the lab is to simply get your objective function into a function of one variable and get an interval for that variable that's in the function. If we have that, then all it amounts to do to finish the problem would be to it ends up being just an extreme value problem. We have a function that we want to optimize. We're looking for either a global max or a global min, so it's an extreme value problem. So we want to do the setup. That's what's new here. So for this particular example, it says, find the dimension of the box with square base with volume 12 and minimal surface area for the first part there. Volume 12 is given and we want minimal surface area. So on these problems, you really want to just start with a picture if we need one for any sort of geometric object here. That picture is going to help you define what your variables are so that you have something to work with. So here we have a box. The box has a square base, and what that's telling me is whatever one dimension is along the base, the other dimension will be 2. And so we're going to use x just for the 2 dimensions that are there on the base. And they're going to be the same because the box there at the base is square. But in general, this box has a third dimension and it doesn't have to match the square base. And so that's a second variable there too. So now when we're talking about these geometric type objects, we have typically 2 different things that can describe the object. And here we could be talking about the volume of this 3-dimensional object as well as the surface area of it. So we need to be able to find a way to determine what it is that's going to be our objective function. So whenever we're trying to figure out what the objective function is, so this objective function is the one that ultimately in calculus you'll be taking the derivative of, finding critical points, and looking for the max or min. But remember what it is we're looking for. We're looking for max or min on these objective functions. So we're needing, when we're reading the word problems, to be able to find some sort of key word that is indicating largest or smallest. So in this particular one, we see minimal as our kind of key word that's cluing us in on the objective function. So for the objective function then, we see that we're looking at the keyword minimal. We want minimal surface area. So our objective function there is going to be the surface area function. I'm going to call it A for area. So we need an equation there that would give us the surface area. Now certainly we have some geometric equations that would be like memorized surface area type problems, but remember this is a box. A box consists of a bottom and a top and then the 4 sides all the way around it. So we can just piece together the areas of each of those faces on our box. So the bottom and the top each are squares, and that square has area x times x, so x squared. And we have 2 of them, 2 because we've got 1 square on the bottom and we've got 1 square on the top of this box. Now that leaves us the 4 sides around the box, and so in each one of those sides the base there would be x and the height of the side would be y, our different value there. And so we've got 4 rectangles, so we're going to say 4 there plus the 4, and each rectangle has area x times y because the dimensions are x by y. So we have an objective function there, area equals 2x squared plus 4xy. And our problem there is we've got two variables. And to be able to do calculus 1 here, we want to optimize this function over one variable over the interval for that variable. And right now we have two. And that's where what we call a constraint equation is going to come into play. So a constraint equation is simply using the other piece of information that's given in your problem to relate the variables in a different way. So what we have for the constraint equation, looking back at what we're given that the volume is 12. And so our constraint equation is going to be our volume information. So our volume overall is 12. So the volume of one of these boxes would just be the length times the width times the height. Well, the length and the width we could say are both x. So you have x times x, which is x squared, times the height, which is y. So we're looking at 12 equals x squared y. That's the second relationship between x and y using the additional piece of information that we were given. So now we've got two equations with two variables in it. And, you know, I guess one of them we really don't have an equation as much as it's a function, but it's a function of two variables, and the other equation has two variables in it as well. So now it amounts to taking one of the variables, or solving for one of the variables in the constraint equation and plugging it into the objective function to eliminate that variable. But then the question becomes, well, which one do you solve for? You've got options. If there's two variables, you could pick either one. That's when I go and I look back at the complexity of both the objective function and the constraint equation for each variable. And so looking at the objective function, I see there's an x squared, there's an x, and then there's a y. So we see in some sense the x is more complicated because it has varying powers of it that show up in the objective function, whereas there is just a single y raised to the first power sitting there in the objective function. And so to me that indicates that I probably want to be solving the constraint equation for y, provided that's not too complicated to do. And actually looking at the constraint equation, in some sense y is simpler because we have an x squared term sitting there multiplied by a y. And if we were to solve for x, we would have to, introduce a square root and be worried a little bit about signs and so forth. And so simply looking at the constraint equation, this one's easier to solve for y also. So that gives us an indicator of what the best approach is. Even though the other approach isn't necessarily wrong, it could be that this one is just more straightforward. So here we have the constraint equation solved for y, and we then go back and we plug that into the objective function for y. So we've got a equals 2x squared plus 4x times the y, and our y is our 12 over x squared. Okay, and you certainly want to simplify this objective function as much as you can first, because you're going to end up taking this derivative, so you definitely want to simplify. So we've got 4 times an x times a 12 all over x squared, so one copy of x is going to cancel, leaving us with a 4 times 12, which is 48, over an x. Okay, and if you wanted to write this as a nice single fraction, perhaps, so that, it amounts to whether you want to do more algebra here before you take the derivative or after. But, perhaps it would be nice to have this as a single fraction. So if we got a common denominator of x, we would not have 2x squared, but rather 2x cubed to balance the x that we're introducing in the bottom, and then plus the 48. And that would be a nice objective function for the area in one variable, x. But now we also need to assess what that interval would be for x. So that interval often comes partly from the setup of the problem with the picture, but also the constraint equation. And so for the interval, we know that the setup of the problem is we have a box. So if we have a box, those box sides are not going to be measured in negative length values. And also, we wouldn't have a box if it had a length of 0 for any of the dimensions. And so right away, we know that x has to be bigger than 0. And we also know that y has to be bigger than 0. So knowing that x is bigger than 0, we need to be able to think, okay, but is there an upper bound for my values of x? Can it just be going off to positive infinity, or is there some cutoff place that we would have to pay attention to? And here, it ends up being that there's not a cutoff place. It does, in fact, go off to positive infinity because, see, as y is greater than 0, we look back here at the constraint equation. Y is bigger than 0, but it can be as close to 0 as we want it to be. And so, see, what's happening here is really the y and the x squared are inversely related to each other. As y gets closer and closer to 0, the x squared, which is in the denominator, would be blowing up to positive infinity. And so what we're really noticing here is that as y approaches 0 from the positive side, because we know that y is bigger than 0 at least, we have that x is approaching infinity, really, since x is greater than 0. So what we really have is that x squared is approaching infinity, but that means x would be approaching infinity rather than negative infinity, since we're starting with positive values to begin with. So that's a little bit on the technical side to get the entire interval 0 to infinity for which we would be optimizing over. Okay? And so this gives us, we haven't finished the calculus problem of it, but at this point we have a function in an interval for which we can now find the global minimum of this using our calculus ideas. And so we're going to take this same object for our part B here, but what we're going to change is what's given and what we want to find. So this time, instead of being given information about the volume, we're given information about the surface area, and we see that key word. This time it's not minimal, but this time it's maximal. That's going to clue us in on what our objective function should be. And so we see the keyword maximal there, which tells us our objective function is going to be a volume function, because we're looking for maximal volume. So we already have talked about this object and what the volume of the object would be. It's x squared times y, length times width times height for this box here. And again, we see that we have two variables. So we're going to need our constraint equation. And our constraint equation is going to be our surface area. Because the surface area is what the other piece of information that was given about our object. So that surface area here is 20, and we already learned that the surface area is really going to be the 2x squared. That'd be the area of the top and the bottom, hence the 2. Each one would be x squared. And then we've got the plus 4 times the area of each side. Each side would be an x by y rectangle, so it would be xy there. Okay? And so again, we look at the complexity of the variables in the objective function and the constraint equation, and again, we're going to come up with the fact that we really need to solve for y in the constraint equation, because it only is there once. X we have as squared and just as x, and so we're going to be in a more complicated situation if we're going to try to solve for x. And so we really do want to solve for y. So here we're looking at, 20 minus 2x squared is equal to 4xy if we subtract over the 2 x squared. And we've got, we want to divide both sides by 4x, so we're looking at 20 minus 2x squared over 4x to get that y by itself. Now, right away we see that we can pull out a common factor of 2 on the top, and that would match with a factor of 2 on the bottom. So really what we're doing is we would be dividing top and bottom by 2. So our y then is going to equal, it would be 10 minus x squared all over 2x. Okay. So what we do with that is we take that and we plug it in for the volume equation. We've got volume equals the x squared times y, and our y was the 10 minus x squared all over 2x. And we see as we're trying to complete this that there's an x squared out front, which is understood to be on the top, and there's an x on the bottom. And so we can cancel one copy of the x out, leaving us with just x times our 10 minus x squared all over this time 2 because the x canceled. And really, I mean, that's actually pretty easy to work with since there's no variable there on the bottom. You might even want to just see this as 1/2 x times 10 minus x squared here. And so perhaps you'd even want to distribute that out so it's a nice polynomial-like thing. So you've got a 1/2 times 10, which would be 5, and then the x tacked on, and then you'd have minus 1/2 x cubed. And that's a pretty nice volume function, and it is in a single variable. So now what remains to show is that we need an interval. So let's write the interval over here. The interval we again get from partly from the constraint equation and partly from the setup. Our setup was that x is bigger than 0 and y is bigger than 0 to begin with, because those are each side lengths for this box. And so this y bigger than 0, we know what y is. That's what that really is telling us, is that the 10 minus x squared over 2x is bigger than 0. But if you take a look at what's happening there, we know that x is bigger than 0 to begin with. So since x is bigger than 0, the 2x is bigger than 0 always. So we know always that that bottom is bigger than 0. So we're really looking at the 10 minus x squared being bigger than 0. And so really what that's telling us is our x squared is going to have to be less than 10. And so the one thing you've got to be a little bit careful with here is when you're solving nonlinear inequalities, technically speaking, we've always gone back to, number lines and looking at intervals. But we're actually simplifying our situation a little bit here because we already have the fact that x has to be bigger than 0. So what's really happening here is as y approaches 0 from the positive side, what we end up getting is that x squared is approaching the 10 from the negative side. And so what ends up happening is that x ends up approaching root 10, really from the negative side. And so what that's doing is that's giving us our upper bound for this particular one. X has to be bigger than 0, but it definitely has to be less than root 10. And so our interval then is going to be the 0 to root 10 for our variable x, which is the only variable we had in our objective function.